Molar mass concepts and calculations. So the masses of atoms on an individual atomic scale, these are measured in atomic mass units, so AMU, or sometimes just U for short. And again, that's the weight of an individual atom. Now, these are a comparison value. So when we see the AMUs, like we saw when we talked about isotopic abundance, they're a relative value, and we use carbon-12 as our basis for that. So these are, and again, the ones you see on the periodic table, they are averaged due to the different isotopic abundances and the ratios of those and some nuclear binding energy and all of that. But these are the masses of the individual atoms, and it is a relativistic weighting of these atoms. So the mass of an atom measured in mu is a relative value. So we can see that the mass of a single hydrogen atom is going to be 1 AMU, and it is based on carbon-12. So we have decided that the weight of carbon-12 is going to be the standard for the masses in chemistry, and since it has 6 protons and 6 neutrons, we're going to say that it weighs 12 atomic mass units. Now, a hydrogen atom having only 1 proton is going to be 1/12 of that, and so carbon-12 is the basis for our measurement, and then whatever the weight of the hydrogen is, it is 1/12 of that weight. So this is how we come up with our atomic mass units relative weighting scales for atoms. Now, we're going to be talking about molar mass today, and so we're going to be looking at the concept of the mole and how it is related to the mass itself. So let's do that comparison. No matter how many atoms you're dealing with, these relative masses will not change. So if you have one carbon-12 atom, it weighs 12 AMU, and you have one hydrogen atom, it weighs 1 AMU. So that is a 1:12 ratio. If you had 2 atoms of carbon, they would weigh a total of 24, and your 2 hydrogen atoms would have a weighting of 2. And so the 1:12 ratio is maintained no matter how many atoms you're dealing with. So 1 atom of carbon is 12 times the mass of 1 hydrogen. 2 atoms of carbon would be still 12 times the mass. As long as you had 2 atoms of hydrogen, you're maintaining that 1:12 ratio between the hydrogen and the carbon. So if you had 500 atoms of carbon, you're going to have a ratio that again is whatever the mass of carbon is 12 times the mass of that hydrogen atom here. So you can change the amount, the relative weighting stays the same. So of course we can bring this all the way up to the amount that you have in 1 mole. And so therefore, if you had 1 mole worth of carbon atoms and 1 mole worth of hydrogen atoms, it is still going to be a 12:1 ratio of carbon atoms to hydrogen atoms. So the relative weighting remains the same, whether you're talking about a single atom or a whole mole worth of atoms. So as long as we're dealing with the same quantities of these different atoms, the relative masses stays the same. Therefore, the mass of a mole of carbon-12 is going to be 12 times the mass of a mole of hydrogen-1. Now, this gets us to our molar masses. So this is the mass elements, is the mass in grams of a mole of atoms for that particular element. So if you had a mole of these atoms, how much it weighed, that is the molar mass. So the mass of a mole of whatever it is you're talking about is the definition of a molar mass. So an element's molar mass corresponds to the element's atomic mass units. The relative weighting is going to be the same. So what that means is if you're dealing with an element like boron, whatever its atomic mass is in atomic mass units will correspond to its molar mass as well. The relative weighting of the atomic mass units is going to also transfer to the relative weighting of the molar masses. So the molar mass of boron is also going to be 10.81, but it's not atomic mass units, right? Because we're not talking about the same scale here. We're talking about the mass of a mole of them. And it's going to be the same relativistic value. So it is going to be 10.81, but it will be the mass of 1 mole. So 1 mole of boron weighs 10.81 grams. So if you had helium, If its atomic mass is 4.0026 atomic mass units, and depending on which periodic table, you may have more or less significant digits, maybe rounded slightly differently, or the samples may be slightly different. They gave that particular isotopic ratio, so it'll be somewhere around 4. But whatever it is, the molar mass for that, the number is the same. The units are different, though, because we're not talking about the mass of an individual atom anymore. That's atomic mass units. With molar mass, we're talking about the mass of a mole of those atoms. And the numerical value is going to be the same because it is also a relative value system, just like the atomic masses for the individual atoms. So if you had 1 mole of helium, it would weigh 4.0026. And again, the units for molar mass we would put at grams per mole. So either you can write it out as a sentence, or you can say the molar mass of helium is 4.0026 grams per mole. So the molar mass of compounds, a compound being made up of more than one type of atom, you just have to sum the molar masses of the individual atoms. So the molar mass of a compound, take whatever atoms are in it, add them together, and you will have the molar mass of that. So essentially it is a sum of the molar mass of its atoms. Molar mass of oxygen then, and again, we have, this is not a compound, it's still an element, but we have 2 of these oxygen atoms joined together. So the molar mass of 1 oxygen is just under 16. You have 2 of them, so then you would be multiplying 16 by 2, or feel free to add it twice. Either way, you're going to end up with something pretty close to 32 grams per mole. So what that means is a mole of oxygen, 6.022 times 10 to the 23 O2 molecules, would weigh 32 grams. The molar mass of O2 is 32.000 grams per mole. Not getting into density and how much it would actually weigh, this is mass. So water, we've got the formula for water. You know there's 2 hydrogens, there's 1 oxygen. So if you want to know the molar mass of water itself, you've got to take the molar mass of hydrogen, you've got to double it, add the molar mass of oxygen, and you should end up with 18.02 grams per mole as the molar mass of water. Therefore, if you wanted a mole of water, you could weigh out 18.02 grams of it. That would be a mole of water. If you wanted 6.022 times 10 to the 23 molecules of water, you would have to weigh out 18.02 grams, and that would tell you that you have 1 mole of water, or 6.022 times 10 to the 23 molecules of water in 18.02 grams. The molar mass of water, 18.02 grams per mole. Potassium chloride, you've got 1 potassium, you've got 1 chlorine. Take the molar mass of each one, add them together. You've got your molar mass of that particular compound at 74.55 grams per mole. 1 mole would weigh 74.55. So try this one out. Pause the video, see what you get. Hopefully you counted your sodiums, of which you have 2, your sulfur, of which you have 1, and your 4 oxygens. Add them all together, and you should end up with somewhere close to 142.05 grams per mole. If you wanted 1 mole of these sodium sulfates, you would have to weigh out 142.05 grams of them. That would give you 1 mole. Realize in terms of the entities we're talking about here, this is an ionic compound, so we're looking at, this is the lowest whole number ratio of the ions. So we would say that you have 6.022 times 10 to the 23 formula units of sodium sulfate. This is not an atom, it is not a molecule, it is a formula unit. It is the lowest whole number ratio of the ions in the compound, and so we would say there are 6.022 times 10 to the 23 formula units of sodium sulfate, and if you had that many of them, they would weigh 142.05 grams per mole. So we've got 3 variables that we're essentially talking about here. Mass, the symbol for it is little m, and we are going to most likely be measuring it in grams. Number of moles, we're using the symbol little n, and of course the unit for it is mol. Don't confuse the variable symbol with the unit. The units is what is written after the number itself. So if you had 1 mole of water, it would weigh 18.02 grams, meaning that its molar mass, and make sure you capitalize it, this is a capital M here for molar mass, its molar mass would be 18.02 grams per mole. Since 1 mole weighs 18 grams, then the molar mass would be 18.02 grams per mole. I'm going to intentionally not give you the formula for calculating between these 3 units. If we do want to calculate from mass to moles, then we need to know the relationship between mass and moles, and of course that is the molar mass. We can use the molar mass as a conversion factor, so we can convert between mass and moles or moles and mass by using the molar mass as a conversion factor. It is the ratio of how much mass there is in a mole or how much 1 mole of the stuff has a mass of, weighs. So we can use it either way, and it depends on which number we're starting with as to how we'd want to set up our conversion factor. Again, we're always trying to put the unit we want to get rid of on the bottom so it can cancel out. So if we're starting in moles, then we'll put moles on the bottom. If we are starting in grams, then we will put grams on the bottom. So let's say we wanted to find the mass of a certain amount of silver. So here we have 0.6800 moles of silver, and if we want to know how much that would actually weigh, and we're using weight and mass interchangeably here because we're still on planet Earth, and so we want to find out how much 0.68 moles, sorry, 0.6800 moles of silver would weigh. So again, we want to set up our given first, and we want to write down what it is with the unit. We then want to set up our conversion factor that will get rid of the units that we are starting in and will go to the units that we're looking for. And it is asking for mass, so we should be ending up with units of grams as our mass here. We put the unit we want to get rid of on the bottom, the unit we want to go to on the top, so it gets carried through to the end here. And then we put in our numbers. We know for silver particularly, the molar mass is 107.87 grams per mole. We put moles on the bottom because then it will cancel out. And units of grams stays. We then do the calculation, 0.6800 times 107.87, and we should end up with 73.35 grams. Again, set up your conversion factor. Don't bother yourself with triangles or equations. Let the units do the work, and they will get you to the answer you're looking for. Feel free to make a therefore statement. So with this one, find the number of moles. So we are looking for moles, and we are starting with mass, and we are talking about sodium chloride. So again, you're going to be starting with the given number. We need to find out what is the molar mass of sodium chloride in order to be able to use it as the ratio to go between, actually here, mass to moles is what we're going to do for this equation. So we've got to know the molar mass of sodium chloride. Then you can take our given value and again include the units for it. Set up our conversion factor, so the units you want to get rid of, in this case mass, are going to cancel out. Moles will then carry through because that's what we're looking for. And then it is just a matter of plugging that into your calculator. 12.34 times 1 divided by 58.44 should give you 0.2112 moles of sodium chloride. Good idea to put the label of what stuff you're talking about as a subscript after the unit. Definitely have the unit so you know what you're talking about. And again, you don't get to choose what the unit is. The math chooses what the unit is. Grams canceled out here. The moles did not, and that is why we're talking with moles. Not because we just want to. We set up our math so that that will work out, but you don't get to force the unit to be what you want it to be. The math determines it. So it's important to set up the math in a way that works out to give you the unit that you want. Put the label of what it is for when we do reactions later and you've got a couple of things going on. You want to be able to track which one's which.